Each registration is unique and grants the right for the individual registrant only to view this webinar. Sharing this webinar with unregistered viewers either during or after its performance violates Pharmatech Associates copyright and is prohibited. Next. If you have not already done so, we ask that you take time to read the Pharmatech Associates course disclaimer. You can download this presentation, including the disclaimer, from your USB education account. Please follow the instructions in your confirmation email to download the presentation. Next. Welcome to today's USB Pharmatech webinar, PCM Measuring Content Uniformity with PAT and RTR. Thank you for taking time out of your busy schedule to join us. Next. Presenting today is Richard Steiner, Pharmaceutical Continuous Manufacturing Lead, and Dr. Pauli Da Silva, Director of Advanced Pharmaceutical Technologies at USB. Welcome and thank you both. I will now hand over the presentation to Mr. Steiner.
Yeah, hello everyone out there, and many thanks for the kind introduction. And I think this is already mentioned. We will talk about today measuring content uniformity with PET in continuous manufacturing regime. And I'm very proud to have my colleague Pauli Da Silva with me. Hello, Pauli.
Hi, Richard. Glad to. Can you hear me? Oh yeah. Yeah. Yes. Glad to doing this webinar with you.
Yeah, will be exciting, and I think we can go ahead directly into the agenda of today's talk. Little high-level summary about control strategy and PET, why this is important, before we will dive into sensor technologies. This will be a part Pauli will leading. Then we will have a look into the current technical solutions on the market for content uniformity measurement, what this has to do and how this works together into a real-time release strategy will be topic number 4 before we go into a conclusion. And so, not to lose any time, let's just jump into this first point. So implementation of PET is discussed since a long time, in particular when it comes to continuous manufacturing, and why this is important, looking to quality by design approach and how this is supporting the quality of your product. Is one of the topics I get many times questions on. What is different to the current state of a batch process, to why and what might be different in the continuous regime, and to what extent. And this is where I borrowed this little chart here from Siemens, a iPad team, which kind of summarizes it very nicely and very simplistic. So in a batch process today, of course, all raw materials have their variabilities in the input, but you have a fixed process which basically works to a certain specific time measure until it's finished, and then it goes on to the next unit operation. So what you will then test in between is whether the quality of your material, the quality attributes are met or maybe out of spec. And then the question, do I still can release the product for the next unit operation? Does it pass or fail? And so there's a constant work to do during the entire process down to the finished product. And now here the big difference and paradigm change for continuous manufacturing, whether this is a drug substance or a drug product, by the way, doesn't really matter at this point. You have a very dynamic process which can or should be capable to react on changes. But how to measure this is the point. So you need PET technology, whether they are sensor-based or soft PET, to react to the changes and to make sure that the product quality remains within the specification. And so you have actually a good opportunity to make a real-time release happening. And I think this is what we will touch a little bit later on, but it's important to give this kind of perspective before we dive into these elements. It is important insofar that you always need to consider whatever sensor technology you apply needs to be in a position to analyze fast enough to interact with the process. In particular, when it is an inline PET tool. And so I want to set the scene with that. If you select the PET, of course, it needs to be appropriate and representative for the case. So you select not only which sensor can do the analytics properly, but also you have to see whether you have the right position in the process where you put the sensor in. You have to define methods of calibration, but further on also development of the models and the maintenance of those related to the sensor technologies. So these are important steps to go. That's the point where I already want to hand over to Pali, because I think she will give us some perspective to what is currently, let's say, on the market for sensor technologies. Pali, this is your part.
Yeah, thanks, Richard, for setting the stage for PAT and sensors. What's their role in continuous manufacturing? So for me, in a way that continuous manufacturing and PAT, they go hand in hand, because you need technologies that can capture the variability of such a dynamic process, and take the measurements and give the feedback in a way, feed the information in a way that you can control the process in a continuous manner. So, and you highlighted very important points when you are selecting PAT tools, right? So for sensors, in a PAT, there's always the spectroscopic. People tend to think, or spectroscopic tools are always the PAT, but there are different categories, right? Spectroscopy-based process analytical technologies and non-spectroscopic-based process analytical technologies. And the choice depends on what critical quality attributes that you need to or you want to measure, and which critical process parameters you want to measure for your specific process, right? And for those two categories, we have good old and essential PAT tools, temperature, pressure. These are non-spectroscopic sensors, but a wide range of PAT that we have seen are based on spectroscopy. So this is across the spectrum of electromagnetic radiation, near IR, Raman, and we also have new emerging technologies that use terahertz and even microwave. But we see the most use cases using near IR and Raman. And they come with different probes with different capabilities to position at different positions. So this is depending on where you want to position the sensor, depending on where you see the most variability in your process. So it could be in line or at line or online. And in most cases, as you have listed, nicely put in this table, most of these spectroscopy-based PAT, you have to use a model, chemometric model, because this is where you use the information that you get in the form of spectral information and feeds it into a chemometric model, and use that to decide whether the process is running accordingly or not, and use that nice closed loop system to not only understand what's going in the process, but to control it real time or in near real time. And if you go to the next slide, so we talked about the non-spectroscopic and spectroscopy-based techniques. Another emerging area that we have seen is the imaging-based technologies. So these could be optical spectroscopy-based technologies. And I think since we are talking about content uniformity, we see using near-IR and Raman technologies coupled with the hyperspectral technology. So in a way that you can get both spatial and spectral information in a high throughput manner. So you get a rich spectroscopic information that gives you what's happening on the surface, or like depth information, which can feed into, again, a model-based analysis to support real-time release testing. So I'll stop there because there's a lot of products out there based on each of these techniques.
And thank you for this summary, Pali. And indeed, I mean, I'm now following this PT technology arena since a few years. And whenever I go to the IFPAC conference, for example, I have to feel there's a new technology coming around the corner. So I think it's pretty important for such a webinar to characterize and to segment these technologies. Also in the light of how fast these sensors can provide results. And this is why I mentioned before that's a key element. How fast can the sampling go? How fast can the feedback to the process be assured? And you see in this column sampling, there's some are offline, inline, at-line. So maybe you can have a short deep dive on what this could mean and which of these sensors you think are more reliable for or fast enough for inline activities or online activities.
Yeah, I think this is where having different types of PAT tools, even for the same technology, right? So near IR, you will see different different probes coming out in the market, whether it's for at-line, inline, or online, to do spectroscopy or imaging-based technology. So there are a wide range that you can choose, and that depends on the process that you are developing, the process characteristics, and the product characteristics. So as the end user, you have the choice where you wanted to implement them. I think with different resolution, different imaging or sampling capabilities. So the trend that we have seen, most of the spectroscopy-based technologies, they have matured enough. Now you see them from development, process development, all the way to the commercial implementation. So this is where most of the inline sampling and inline positioning has been seen. But that being said, there are technologies, let's say Raman probes, that can be better suited for a certain technology or near IR. But then you have this question: technology-wise, it's suitable, but is it operationally viable? Because you need to have the footprint of these probes. Can you position it in your existing flow, existing infrastructure in a way that it doesn't disrupt the process? So in summary, what we have seen is for technologies like near-IR, you see more application and more implementation in line. And for other imaging technologies and other technologies, they are mostly at line. The main reason is not the technological suitability or the capability or the resolution they can offer, but it's just the main barrier has been the footprint and how you can fit it into the existing, hardware.
Yes, that is very important because we will come to this a little bit later, showing some of the technologies available. And I think that's a really important note to make. So it's not just if a sensor can do its job, but it's for engineers then the question how to integrate this in a system. And these interfaces I will elaborate on a little bit later. Okay, so you have typical quality attributes, and I think just as an example, we use an oral solid dosage Conti process here because we talk about content uniformity. I just pick out one because, I mean, talking about all of these would take hours, but we promised in the headline of this webinar to deep dive on the content uniformity. So you see NIR as one of the main technologies. It's well established, and indeed you can see there's also blend uniformity and all of the other criteria. So it looks like NIR is indeed one of the most common technologies used nowadays. And we can also see, if we zoom in a little bit more, you have different kind of NIR technologies. Maybe Pali, you can elaborate on what, for example, is an NIR reflection system looking like?
Yeah, so I think we have seen for near IR, you can have two configurations. You collect the information in a reflection mode or in transmission mode. Again, this depends on your product, right? So whether you have a translucent sample or whether you would like to, whether you see more surface roughness for your sample. It depends on what critical quality attribute is critical for your specific product. So in that sense, you have two choices, reflection or transmission. And for Raman, I'll go one step further. For Raman spectroscopy, we have seen mostly transmission in a way because you have more, you can scan deeper into the tablet, since we are talking about oral solid dosage forms. Yeah, you have the choice of picking which PAT technology again fits best for your process and your product. And they have the similar capabilities. And another factor that you have to take into account is the resolution, right? If you have a low API dosage form or high dosage, your choice is going to be different. So these are the factors that one has to take into account when you're selecting, which one to choose.
This comes right away here. So I think where there's light advantages, there's also usually also some disadvantages. And I think this is what we want to highlight here. It's, of course, NIR is fast, accurate and flexible. We know this. Also Raman and microwave technologies can do the same. But okay, the coming disadvantages with it is the resolution, as you mentioned, but also the window falling is one of the key things. In particular, if you look to long operations, long running operations like continuous should do, you need to make sure that it's not just works for an hour or two, it needs to work for 24 hours or even longer. So you have to foresee possibilities to window clean or to put the sensors into a space where they can't fall. And then I think on top of this, what is required for your product? What is required for your resolution? If we go nowadays, a lot of cases for continuous are driven by low dose formulations. So you have to identify with this PET sensor 0.5 to 5% of the weight average in your low dose application. So what do you think, Pali, is a good technology to go into this kind of segment of application?
Yeah, it's a tricky question in a way, but it's not tricky at the same time, because I would imagine one would do before implement PAT in a commercial setup. You would have to do a lot of research in the development stage, understanding your process and product. And as you mentioned, the durability or the reliability of the data that we are getting from the PAT tool in a long run of a continuous manufacturing line, right? So in that case, I would imagine one having a decision tree for your specific product. And if you have these three choices, reflectance, transmission, EIR, and Raman transmission, you would go about whether I have a product that needs higher resolution, which one you have to outweigh you have to balance the critical aspect that you wanted to measure. That goes back to what I mentioned, the technical suitability, but at the same time, you have to look at everything will work in the development stage, but can we integrate it into the legacy line that I have? Or, you know, if it's Raman, we had a tour at a facility, continuous manufacturing facility, that had this issue that Raman probe gives them the information that they absolutely need in the development stage, but they are having problem implementing in the commercial line because it's not compact enough to implement. So to wrap up, I think there are many factors, but I think having these PAT technologies for continued uniformity, that gives you a rich information to build into your system in a way that you can have end-to-end continuous process without breaking the continuity of testing.
Yeah, and I think that's a good example. I want to highlight another factor which comes into play, particularly if you go to low dose. Usually these low dose applications are also very challenging when it comes to the containment level, because you can see that this is usually a high potent product as an API. So you also want to make sure that whatever sensor you implement, you have to consider what to do if I have to clean, if I have to take this offline for cleaning after window folding happens or curing. So, but this has to also happen in a contained manner, which gives another challenge for the system engineering. Yeah. So, but I think the good news, not to let's say to spread too much doubt, but or insecurity, we have a lot of wide of range of opportunities in the market nowadays. Yeah, to find the correct sensor is nowadays much easier than it was maybe 15 years ago.
Yeah, I think it's a positive outlook, as you mentioned. One has a large array of choices in a way that you can tailor it to your own process or product, and you don't have to, you don't have to change how you are thinking about implementing PAT.
I zoom out further. So this is just, I call it my chessboard. A typical oral solid dosage system starts with material handling. So you have material flowing through to the unit operations, which are just represented here by these squares. And you go through to dosing, blending, granulation, down to the coating of the tablet. So this is quite some ways to go for the material. You have mechanical interconnections between these unit operations, which might be a low-hanging fruit, but in some cases, you have also multiple levels in your facility to cross over. So that's another element of challenge. You have the process itself, because also these unit operations talk in a kind of one to another, saying if I go downstream, how fast I can go downstream with the material, how do I release the material to the next unit operation. You have the controls who is basically overseeing and managing all these unit operations and orchestrating them, that they are harmonized in their activities. And now, as a matter of additional complexity, you have the PAT tools, and they are usually in these interfaces between the unit operations, interestingly, because they, of course, check the quality of the product on the way down the line. And so it is not a surprise. So we will find PAT on all of these interfaces. The one we talk about, content uniformity, is basically down the line before it goes into the tablet coating. But also we find nowadays applications for tablet appearance, for how the coated tablet looks like. This can span over really levels. And if you see earlier installations from continuous manufacturing, you will see that these interfaces are basically an own unit operation out of a sudden. What you see here is called the Christmas tree of an installation in the market, well known, where you see how this could look like. So just in the middle where this hand is basically the sensor. All the rest is to making sure that the sensor is not only maintained properly during operation, it's also to allow sample taking, so to take physical samples if needed in a development process, also to run alongside the sensor steadily the material. Yeah, so it's not just putting the material somewhere in a powder bed. You have to make sure that the material constantly and consistently flow alongside the sensor to not create too much noise. This all has to be contained, plus isolated from other factors like temperature and humidity, etc. So yeah, that's quite a system in its own right. You can find today more simplistic tools for this, also ready to buy basically and to implement. There has done a lot of development progress over the years from the equipment vendors as they understood the needs to make it more easier to implement. But in a nutshell, I think the complexity everybody is kind of concerned about when it comes to commercial operation is, of course, obvious if you see this whole setup. And I want to highlight a bit the interfaces. So I call them interfaces between the unit operations. They have, of course, to transfer the material, the intermediate material. You have to check that this material is within the spec, which the PT is doing. They have mechanically to support the sensor and its supporting functions while cleaning, for example, or whatever happens, or wiping off the sensor. They need usually also to provide some really physical access to the material, because you want to check, see also offline how the material is fitting to what is your expected quality. And yeah, what is sometimes forgotten, you have also to discharge. So there are also discharge gates for out of spec material. One of the, let's say, high level ideas in the control strategy is that only good material goes into the next unit operation. Yeah. So in the case there's something happening, of course, you make sure that this material is properly discharged. Also, ICHQ13 has a sentence for that, saying location of material, diversion and sampling point, selection of the location for diverter valve and sampling point without disturbing material flow and transformation. This is a nice sentence, but it also means if you have, for example, airflow in the system to consider, you do not want to interrupt just by this interface the continuous flow of the material. And that's all a design challenge for engineers. And this is why I want to highlight this. If you talk about reliability of a PAT installation, it's not just the sensor. This is everything around the ecosystem of the sensor, I would say. who are in charge for the reliability of the whole continuous process. You do not want to have a compromise to a multi-million-dollar equipment train just by, oh, there's a failure on the sensor and everything stops. So this is why I think if you look nowadays into solutions which are offered, you see more and more integrated system engineering, which is really important. From the early days when these systems have been, I call them always a bit Frankensteinish in the design, you see that after many years of development, you get more integrated units like the one I show here, where basically within the system you have already foreseen the PET probes, the discharge points, and everything integrated. So what do you think about this, Pali?
Yeah, I think as you mentioned, it having these kind of integrated system, it avoids certain issues and problems one would face putting each individual unit operations into a continuous line. And I think the two other factors that we have to think about here is, as you pointed out, having these interfaces and PAT tools, if one goes off, it will disrupt the entire process. So that means you have to have not only the instrumentation, but a strong, stable data architecture as well, right? So because more PAT tools mean a lot of data, and you have to have more robust, efficient system that goes along with it to process this data in an efficient manner. And then a good control system, I think we cannot forget, those are critical part of it. So one has to think about having all these parts in place
Sure, yeah.
to make sure it, that gives the benefit of implementing these PAT tools and how it works with the existing infrastructure or the infrastructure that you are going to invest in. So I think it's a good innovation in a way that one doesn't have to put pieces together, but it comes as a one system with PAT built in.
And that's a nice reference of yours, and it will come also to this point, control architecture and controls around that, because indeed you collect a lot of data, which is one of the big advantages of continuous, and you have to handle this data meaningfully. But I think what I also found in recent demonstrations, I saw some of these systems, and it's really pretty interesting how fast and how easy the startup procedures can be, and how fast you see the response from the sensors. So it's actually, if you look to this more advanced systems, it's really getting also easier compared to the first years in the process. But we want to talk about content uniformity and how to measure that. This is the traditional USP 905 and European pharmacopoeia kind of approach, of course, based on the ideas of batch manufacturing. So you take samples, you put them on a weighing scale, then you put it somewhere to measure the content, the API concentration, and then you have the uniformity of a dose. So dosage unit, and then you take basically samples. Yeah, this is what is described here, because usually you have then a bin of tablets. You take samples in a certain amount, which is nicely described, and you measure that. I think the European Pharmacopoeia has also put more, let's say, finer look into bigger sample sizes for bigger lots. But in a nutshell, this goes all the same way. And I think the topic is now, how will this change if I go into a continuous operation? And how can I do this same testing online or inline with immediate feedback? And I think that's what we are going to talk about. we had in the early days basically developments like this one here from Bruker. It was called tandem because, as you can see on this little picture, hopefully everybody can see this well enough. You have on one side the typical tablet checker who is doing all the online, the typical tests like weight, size, hardness. And then this device is handing over to an NIR system to make the quality check on the content. This was the early development, and with some of the struggles, as you can imagine, if you put these kind of technologies together in the handling of the product, these are sensitive tools. And so I think it was an early way to go into content uniformity measurement according to these before mentioned standards. But when I talk around to lead users of this technology, they all say, okay, but we still do the typical manual offline testing. We bring it to our, let's say here, the Bruker MP device, and we do it the traditional way. While the process is running, we take our samples. So yeah, what is the fuss about doing this continuously is the question. Of course, this is the gold standard, but you can see, and now I zoom a little bit into one of the suppliers' solution. They have an NIR sensor who is fast enough to measure basically each tablet. The reflectance, so just the surface, but at the same time you have the information available from the blend uniformity of just a little bit upstream. So you could make the correlation between just having the off-light version to the blend uniformity before it goes into the feed frame. Isn't this sufficient enough for measuring a content uniformity? Pali, what do you think about this point? Because they call it not content uniformity, purposely they call it tablet uniformity. But I saw the system and I was pretty stunned how fast and how well this is operating.
Yeah, I think from an innovation point of view, it's amazing that the technology has advanced in a way that they can detect and measure each tablet. That means 100% check or 100% content uniformity testing. But that's a great innovation. But the question for me is it really necessary 100% tablet testing? This goes back to the 905 that you mentioned. That's content uniformity. It's a sampling. It's a question about sampling, and it's a question about whether you have the interpretation is whether you have a process that 100% verified that it's running properly to get the product that you want. I think that statement doesn't change whether you are doing it batch or continuously, because you wanted to make sure that you have 100% verified process that gives you the products that within the specification. So I think these are nice systems to have, but are they needed? Based on what I have seen in from the regulatory agencies, they're not prescribing 100% tablet verification. If you have seen anything other than that, what do you think, Richard? Because I think it's 100% ensuring that the process is verified. Tablet is a nice thing. Yeah.
Here you talk to a continuous manufacturing believer. I would come from the other way around. I would say, okay, listen, this is nice to have, but you have a Six Sigma process. So why do you want to confirm again to have a Six Sigma process? You can do this in development, maybe by tools like what we see here, which is another nice development which I found. And this is really impressive because in this tool you have everything integrated what you evenly can find nowadays. I think they have even expanded the capability of this thing. So you measure each single tablet by all of their quality attributes from the weight, the thickness, hardness, diameter, with microwave, with a laser scanner, and you name it. And they use special resolved spectroscopy to have an even, let's say, more surface area, and in going beyond the just reflection. They go into the tablet, and this by also an unbelievable speed. That's great. I would say this is perfect for development applications. The question is whether this is really applicable for a commercial operation.
And
But
yeah,
the,
and
the market will answer this question over the years.
yeah, if I add a couple of points, Richard, I think there could be instances where 100% continued uniformity could be justified if one see a reasoning. Let's say you know a process that's are prone to higher variability. In that case, if you have this system built into a fully contained continuous manufacturing line, that's where you can use. You have the reason because it's a highly variable system. Or in other case, we have seen for additive manufacturing use cases where the way that the manufacturing works and the output that they're getting, these are relatively small volume output. In that case, you are inherently, the system is built in a way that you can, without much effort, do the 100% continued uniformity testing, even that's built into the system, and it's compatible with the way that it's manufacturing. And then the other question, like I mentioned earlier, is you are getting a lot of data and how you are going to handle it. That's a part of the 100% testing as well.
But yeah, you see also in the design here, this is really a solid machine and a solid system, which is impressive in its own right. And I think this pharma technology company has done a great job to push the boundaries. Yeah, there are other solutions like here from Optimal, robot-based. If you check out this YouTube link, you will find a nice video of that, where a robot is basically, instead of what I mentioned earlier, someone walking around taking samples, here the robot is doing the job. Also a nice automated solution. Or if you have just typical add-line unit operations to do in-process controls, you also find here solutions where the active ingredients are measured by an NIR system within the same device. And I think I did just a small table like this and say, okay, you see here, you have maybe 5 or maybe now 6, 7 options, and each has, of course, their limitations. Interesting to me was the point, if I look to the capacity, and we spoke earlier about how fast are these systems reacting. And you can see here the solution with the embedded PET shown earlier. They are pretty fast indeed. They do about 120 tablets in a second. They all have a little bit a containment limitation. We highlighted that this could be important for the low dose applications. But yeah, this is then case by case necessary to verify. And some, like the pharma technology or the grammar device, they have even the other elements already on their capability portfolio. So yeah, each and everyone, and this is just a showcase here. It's not meant to compare competitively. It's about giving a suggestion how someone who is in the process to select the right choice for his product may need to look into that, saying, put yourself onto such a table, try to find what is important for your product, and then peel the onion from this side. The control parameters, you have already a lot of them on board, by the way. Soft PET. Pali, what do you think about soft PET? What is your take on soft PET tools? Because you have a lot of PET embedded in these systems already, yeah? Like I showcase here on this graph.
Yeah, I would say we have seen more traction or talk around using soft PAT, and this goes hand in hand with building mathematical models, right? And that I would say there are certain guidance that have released that might spur the question how to proceed with soft sensors. But I would say from USP side, to provide guidance, we have released technical guidelines, and we have some under development how to support the industry in terms of not only physical PAT but soft sensors as well. So it's an evolving field. We would like to see what industries and regulatory agencies take on it, so we can provide the guidance as fast as we can.
Because I think we will touch to this at the end, to this point. I think, of course, if we go back to the sensor-based PET, so on top of the soft sensors you have in each of these systems, you have then these sensor-based PET tools, and you need to have a PET management system on it. So you mentioned this as well, that it's important to control and to manage all of that. So you have this overarching SCADA system, and I call it orchestration system, who has to manage all of this. And this is, of course, also some complexity. But there are tools which can help on that. I just name here because I got some material from Siemens. They have their SciPAT solution. There's also others like Optimal out there who have a PT software, SyntiQ as an example. What is this software doing? Basically, the software is there to manage this data stream, to manage the real-time prediction models even, yeah? So when we talk about modeling and models, predictive models, this is where these models are living. They are living in such a software who has to manage all the information coming in from the PET analyzers to feed back to the systems and to the automation system via advanced controls. But, and this is the big but here, these analyzers and these systems have to be fast enough to cope with the speed of the continuous process. And I think that's some of the criteria which also will come into play here. Before we can even talk about real-time release on the back end, you see this on this chart. This is basically how this all then would become one picture. But the but is the complexity, and the but is the reliability of these kind of technologies. Any thoughts from yours end, Pali?
And I think the compatibility as well, right,
Yeah.
Richard? So
True.
that's a big part to building these mathematical models that will ultimately become soft sensors. There's a lot of work that going behind the scene, like how compatible these PAT tools and the sampling frequency with the process dynamics, and maintaining these models. So yeah, that's that definitely supports the real-time release testing, but there's a lot of science-based, risk-based work that has to go into it.
So you have actually three levels of that. You have the sensor-based models, you have the soft sensor-based model, soft sensors, and you have the predictive models, which we we need to have an eye on, because some say, okay, can't we possibly run such a technology just on predictive models? And there have been showcases like this case here from, I think it was Merck Sharp and Dome together with Gea, who worked on this. So they showed a very nice application for just predictive model. Is this enough? Can you just run the commercial system even without PT, just based on the predictive model? I think here recently the FDA came out just in January of this year with the 21 CFR 211-110. And this is a very interesting draft to digest for everyone out there. So they've been pretty clear here. Of course, it is helpful to have a predictive model, but we still expect that someone applies PT. This draft is also interesting to read for other purposes. Here, for example, this gives you some options to say, okay, maybe you can combine one or two or more unit operations as a single unit operation, to say it's maybe some possibilities to use blend uniformity and where to measure blend uniformity in the feed frame or after. I scroll through to this. Everybody can read this themselves. What I want to highlight here, and this is, I think, was for me at least one of the takeaways. Therefore, control strategies that rely solely on current process models would be insufficient to satisfy the requirements. So I'm not sure, Pali, how you would read this, but to me it reads like, yes, you can apply predictive models, but we have not seen that predictive models are always reliable enough. We still expect industry to use PAT as an additional element in this.
Yeah.
Okay, because also of the time, but I just want to show that if we talk about predictive models, this is possible, but also here in the guidelines, it's always mentioned you have to have additional analytic technologies online or inline to measure critical attributes like the potency, like the content uniformity, and just go through to all the guidelines, whether this is the FDA's perspective or the EMA's perspective to the topic. And they highlight this in their regulations. When it comes to real-time testing, we can, of course, rely on predictive models, and we do this, but we want to get additional clarity on the quality of the data, the reliability of the models. But again, I want to pitch back saying, okay, you have a continuous process. You know, continuous process means Six Sigma, and cases showing this. The process capability is maybe an index to look at. If you showcase that your process capability is in the Six Sigma range, which means 3.4 defects in 1 million tablets, someone has to imagine that, just to give a perspective to that. So why do you want to have 100% control? Maybe a nice way out of that is what we would suggest is saying, okay, you can use your operating characteristic curve, a tool, to optimize the sample size for your Six Sigma process. It's a statistical tool, but you can use this to see what is really actually the sample size I need for a Six Sigma process, not just relying on the 10, 30, 20 samples you have in the USP. You simply use this tool to define it for your specific case. And with this tool, you can do that. And I think this is the suggestions, one of the suggestions I would draw, saying, of course, you have sensors who can give you everything, but hey, you don't need 100%. Make a conscious and risk-based decision and use this kind of statistic tools to help you on that. And the conclusion to this, still 5 minutes left. This is something I picked up in the discussions with lead users. someone was saying the irony, much higher transparency, showing the control of the process, while at the same time measurements are showing our process is Six Sigma capable. So this is a lead user saying, if there's any product we shut off all the complexity, we would still have a Six Sigma capable process, which shows the reliability they found in the continuous process. So this is the reason why we have continuous processes. And this is why we push for continuous processes. A lot of work has been done to demonstrate this capability, but created the complexity of the control strategy in the filing today. And that's now a little bit the perceived hurdles and struggles for some saying, oh, we opened the box of Pandora. So why not relying on what we know? But of course, we have to showcase. And I think that's the quintessence of what Pali and I discussed today. Maybe, Pali, the final thought from your end before we open for the discussion and questions.
Yeah, you sum it up really nicely, Richard. I think at the end of the day, with PAT tools or sub-sensors, in the end, when you're doing the filing, you have to have, it's an evidence-based, data-driven approach. You have to show that you have a nicely validated process and a product. So all the decisions that you take before that, it's the back, you have to have that in mind when you're implementing PAT tools or for content uniformity or real-time release, that decision is governed by what the filing needs. So.
Okay, now let's see, what questions do we have? I see the first one, to measure content uniformity in a continuous manufacturing. What PAT sensor technology should be used?
Richard, can you go to the next slide, please?
Oh, yeah, sorry. Okay, this is the one. All right, thank you. Sorry for skipping. Yeah, so Pali, what would you suggest?
To measure content uniformity. So again, that depends on which PAT sensor technology to use or should use. This is a question based on the process and the product, right? So again, how variable your process and how much sensitivity you need in testing your product, whether it's, we talked a little bit about whether it's high dose or low dose. That based on that, it depends on, based on those factors, you can choose which PAT tool to use, right? And then the, whether it's near IR transmission or reflectance or Raman PAT could be the best fit for one's process. So again, that depends on the product and the process dynamics, I would say. But in most cases, it has been, I believe at this point, it will be either near IR or Raman based on the maturity of the technologies that we have seen. What's your take on that?
Yes, absolutely. I think this is a point I also can highlight, that there is luckily enough technology out there, and even combination of those. I think that's doable, possible, and goes straight to the next question, saying, is it necessary to measure 100%? I think we are. Hopefully, we answered at this point already. If not everything which is possible is also recommendable for a commercial application. Indeed, it's nice to have, but I would say for continuous process, I would say it's not necessary to do 100% testing. If you have the capability to do so, take it and use it. If this is reliable enough, I think yes.
Yeah. And I think another one related to that, how many samples do you need in continuous? Again, this depends on, this is a question about sampling frequency and resolution. that you need, that needs to be aligned with the process dynamics in a way that you can get a representative, statistically representative and relevant sampling.
There's a interesting question for you, Pali. How to do life cycle model management? What detector, when the detector is changed, and how to validate existing PLS models. So in other words, what to do if I have to change my NIR?
Detector, what if the detector of NIR has to be changed, and how to validate the existing? So the model, because we are talking about changing the spectrometer that used to build a model. So in that case, the spectrometer that comes with the resolution and the speed of data acquisition, they all change.
So you have to revalidate.
You have to revalidate it. Oh, yeah, because you are changing the important parameters of the spectrometer.